with basis function expansions. So let's just recap what we covered the last time. The linear regression with the basis function expansion is extremely simple, and it's totally this. Everything else is the same as linear regression. The task, the formulation, the optimization, and the coefficient properties. The only differences is the relationship of y and x. So we just perform a very simple expansion by expanding the x into phi x, and that's all it does. And this phi x is, in fact, the user designed it. And we covered polynomial regression on Tuesday, and then there are many possible basis functions. So one of the very clear question to ask is just which and what type of potential function can be a good phi function. So we kind of quickly covered there are a lot of popular basis functions. I mean, for example, polynomial is what we already covered. So in the polynomial basis case, we actually have only one hyperparameter to select, so which is the d. So what is the largest degree of polynomial terms that in your phi x representation that you want to include? And then there's also other kind like radial-basis function, sigmoid function, spline function, Fourier function, or wavelet function. So each one kind of this type of functions, they have some like hyperparameters. So I will talk about their hyperparameters and in the next few slides for this radial-basis function case. All right, so just to put RBF radial-basis function and sigmoid function like side by side, and their equation, it's in fact a little bit hard to remember, but just geometrically, actually just remember the RBF functions look like a bell-shaped. So here it's a little crowded here, but let's just kind of. So it just each one possible basis function, RBF basis function, it's just a bell shape. And the difference is just the center. And also we're going to talk about it is also the wideness of this bell. And the sigmoid function, we're going to use this a lot in the later deep neural network sections. And just remember sigmoid function, those function has S shape. It's pretty intuitive. Those function has S shape, kind of squashing from positive infinity and negative infinity to a bounded range. So this is the sigmoid function family. And we're going to only cover RBF, and we will cover sigmoid later. Okay, so what is radial-basis function? Radial-basis function, the mostly used, it's the Gaussian RBF. It has this specific function form. So you can take exponential, and the inside, so your parameter is this x, and there's two hyperparameters here. One is lambda, control the wideness of your bell, and then the other is this gamma, controls the center of this bell. So the equation is just x minus r take a quadratic, and then over this 2 gamma quadratic, and then inverse. And this is actually, in fact, just a Gaussian distribution, is like just a Gaussian function. And let's look at one-dimensional case. I mean, it's like this kind of hill shape, and when you have a two-dimensional, when your x is two-dimensional, so like, let's see, so this is always this vertical axis representing the k, the value of k, kx, and this representing the value of k2. The vertical is the k, the value is x, and for a specific that gamma, and then this also for that specific gamma, and the y-ness lambda. And this is a vector two-dimensional case, and this is a scalar one-dimensional, the left and right. All right, so let's dive into even more the details. So if we just do a calculation, when your x equals to gamma, it's actually very, very, very simple, right? Because gamma minus gamma give you a 0. Exponential 0 is 1. So which means if you are the x at that center, and this kernel, we actually normally call this RBF kernel, the value of this basis function is 1. So at the center, it's always 1. And if you go to the left or the right, because this is a symmetric function, so go to the left gamma or go to the right gamma, so like just, actually not gamma, lambda. This is the y-ness. If you go 1 lambda to the left or 1 lambda to the right, and this give you the same k value, the kernel values, which is 0.61 roughly. And if you go 2 gamma, it give you about like 0.1. If you go 3 gamma, 3 lambda, sorry, always the mistake. So if you go 3 lambda, this y-ness, this kernel and this function value, it's almost close to 0. So which means what? So, and there's just no values when you 3 lambda apart from the center. So think about, you're using this as a basis and to construct some function to approximate some values. And for it, this type of function can only contribute when that x is within the left 3 lambda and the right 3 lambda range. More than those, and there's just no way this kernel function, this basis function contributes anything, because it just equals to 0. No matter how larger you have a weight, have a theta here, no matter how large is the theta there, I mean, it's just, there's no way, it doesn't matter the size of the value of the theta, when the x is beyond, either it's larger than gamma plus maybe 3 lambda, or smaller than gamma minus 3 lambda, no matter what is the theta actually controls the contribution of this basis function, it always just contributes 0. So this actually tells you it's a very localized contribution, localized, centered at the gamma, at the center, and then as the as you far away from that center, it just very quickly, the contribution, the influence of this basis function just decreases a lot. So that's about it. All right, so let's use this type of basis functions to approximate my data. And when we use this type of RBF, radial basis functions, and for each of the radial bases, we need to specify its center, and we need to specify its y-ness. So now, oh, sorry, there's a little typo here. So this should be gamma, not mu. Yeah. So we need to specify for each phi j, and we need to set what is the gamma j and what is the lambda j, what is the center and what is the y-ness of that bell. So assuming let's use maybe 4 basis function to approximate my data, and then the phi x really just represented as this. So 1, first k, k lambda 1, gamma 1, then second k lambda 2, gamma 2, until k lambda 4, gamma 4. So we actually can tell, when we use this basis representation, we need to learn actually this theta 0, which is the intercept. We also call this bias. This is the bias term. And we also need to learn the theta, the weights on each of the k, on top of to weighting each of those radial-basis kernel functions. Because we designed 4 kernels, and then we need to learn 4 weights plus a bias term. So together we need to learn 5 theta, size 5 theta. So, but at the same time, we actually need to pre-design a lot of hyperparameters in this case. So it's weird, doesn't allow me to draw. So for that, we need to have the gamma 1. Okay, let me draw under gamma 1, lambda 1, gamma 2, lambda 2, gamma 3, lambda 3, gamma 4, lambda 4. So this is called hyperparameters. It's called hyperparameters, and the theta is the parameter of our model that we use optimization to search to fit on our data, and you need to select, and there's another group. This is called hyperparameters, the lambda I and gamma I group. And then here is the weights and bias. All right. Okay. It's a little bit over on top of each other. I'm going to clean the code, clean the slides later. All right. So yeah. Okay. So yeah. So this is my so no matter what, in the end, you use the same equation, like normal equation based, or stochastic gradient descent, or gradient descent based, to solve just the same as linear equation. The only difference is you change that X matrix into the phi matrix, and that's it. There's no other differences at all. Okay, so now let's see a concrete example. We are having this given data, and yeah, so because I'm eyeball just to check the data, I'm thinking, wow, okay, so maybe I can design 3 RBFbasis just because it looks like three bell shape, because this may be 1 bell shape. So assuming this is 1, so let's assume this is 1. So maybe I can have a bell shape here, and then I can just use weight to push it up to fit all the other points. And I can have another bell shape here. Maybe here, and then, yeah, maybe here. And then I can have another like bell shape here. And the wideness is a little, it's a little narrow, the first bell. And also we don't want the wideness to be too like close to 0 at this 2 bell, because there's no way you can fit the points here if both kernels close to 0 at that point. And those are not good choices, because both kernel close to 0, and then it's very difficult to fit the points here if they have. So there needs to be a little bit of overlaps, around the kernels. Yeah, maybe a little wide here, a little bit wide here, and then a little bit wideness here. So this is my design of the kernels. They should all be 1. So okay, I moved the 1 here because that's just when you center at the gamma, it's all give you 1, right? All right, now let me fit theta. So I will not do this, but this just roughly, it's more like eyeball speculating. So the first one gave me a minus 0.5, and then the second almost like a 5, then the third gave me roughly 2, and the wideness is kind of different from each other. So it's your choice about lambda and gamma, and lambda and gamma. And the weight is learned. And in this formulation, I actually did not even put a bias term there. So for some cases, you actually can just you can just specifically set, I don't want to learn bias. So like this case, but you also can learn bias, like a theta 0, if it's pretty off, like in that center, in this point. Yeah. All right. So this is just like eyeball to show you how to do this kind of RBF-based regression fitting. I think next I'm going to show you a code run just through a Colab notebook. I will stop my slide share and then go to I think this is my L5. So in the slides, in that original page, I actually share you the link. So this is the RBF or regression notebook code I modified from this Python data science handbook. So I think let's see if it runs well. So again, just load the library, then generating data, and always plotting your data. So this is actually a pretty complicated function. It's a sin x function. So, and I sampled only like 50 points. So this is about 50 points, and to plot it here. And then the relationship from x and y, it's the sine relationship. There's plus a noise, so this is a Gaussian noise, a little bit of noise. All right, so this is my data. So how can I fit? This is an extremely complicated relationship from x and y, right? And so if you still remember that polynomial regression Python notebooks we wrote, we actually ran last time. I think I had it here. So last time we told you, I mean, it's very simple how to do a polynomial regression. You just reuse everything from linear regression, but only so using this pipeline wrapper, and only changes this feature using this polynomial feature generator. So, but in the RBF case, I think there's no RBF feature generator. So you just write a class, I mean, generating this Gaussian RBF features, which is actually pretty simple too. But remember, in the RBF case, we need to specify the center. We need to specify the wideness. So let's see what it is. This we will go over this code a little bit later, but let's see how do you fit. So again, think about there will be this Gaussian feature generator, so generating those phi x for you, and so there's a hyperparameter is 20. It selects 20 centers, and then around that 20 centers has a small, very small bell wideness. And then if you use this type of feature generator, and you again using everything the same as the linear regression pipelines, and this is how you're going to fit. And so this is your Gaussian model. This is RBF model fitting. And then this test data, it's just you sample from 0 to 10, like 1,000 uniform distributed X tests. Then you fit it, and this is what you get. And so this actually can show you, and this type of RBF-based kernel fitting is actually very powerful. So it can fit very, very, very complex relationships. So let's come back to see this Gaussian feature generator. So like I told you, you need to select gamma for each kernel, each basis function. You need to select the center, right? So this is a pretty simple way to select it. They just use, uniformly, they just create n centers and uniformly sampled from the data range, from the mean to the max. So this is one way to automatically select the center. And I think this is a specified wideness, if I remember correctly. Yeah, this is also calculated just from the neighbor center, and then you're just using a wideness like scaling factor, like 2, just a little bit wide. Like I told you, don't make them completely just about center to center. There should be some overlaps, because otherwise there's no way to like model this point, like seems to in the lower point, the valley place. Yeah. All right. So this is show you one case to how to automatically generating centers, select centers, and also select wideness. All right. So we see this, right? This is like picked 20 centers. I really want to show you one thing, because this Gaussian feature generator already hide the gamma and lambda choice, but there's still one hyperparameter to pick. Very similar to the polynomial case. In the polynomial case, you need to, let's see if we still have that curve. Yes, here. So in the polynomial regression case, you need to have this largest degree D term, right? That you need to define it. And then in the RBF case, similar things, you need to define how many centers. So we show you a results from a 20 center, and that's from a 30 center. So it just, wow. So after you change it to 30, just suddenly, and the fit becomes so bad. I mean, there on some point it's actually better than before, but on some other point it's just so bad. So look at this. I mean, it's just like it have this kind of bell shape. It looks like completely from nothing, right? It's just really in the end, because you have such a narrow bell, and that bell just try to fit exactly here, actually in around this region, but this region has no training data to tell this Gaussian kernel how to behave, and it just behave according to the two boundaries, and then in the middle just go kind of wildly, go pretty wild. So which means it needs to be very, very careful. So this type of RBF-based kernel feeding is extremely powerful and flexible, but it's also very, it needs careful controls. Yeah. So think about almost like on every point I'm feeding a RBF and around its center, and then and go around that data point a little bit, and to smooth out with the neighbors. And in fact, I mean, a lot of people see in deep learning, it's almost doing the similar thing on the high dimensional case. So keep this in mind, and we're going to revisit this concept later. All right, so remember this. If you have too flexible models, at some regions there's no good training point, we don't have enough training points, the model will behave really wildly, because it just doesn't know how to behave, because you don't give supervision in there. All right, let's just see one more. I mean, I think this time so this is trying to show you, because it's more like you're putting this bell at, there are many bells, right? Let me see if I can draw here. So it's equivalent to, I'm having a lot of bell. I'm just feeding a lot of bells, like at every position, and then do a weighted sum of those bell shapes to feed my data, right? So for each bell, I have a theta, so which is exactly what we reviewed. So for each, and this is the theta for each bell. And you can actually tell, I mean, at these regions, and when you don't have a lot of training data, and the theta got really large, I mean, large and small. So they're so close at the locations, but this one bell got a super large contribution, and then its neighbor bell just got a negative contribution. And this means what? It just means, it's just too flexible. I mean, the model doesn't know how to behave. So they're kind of the two really large positive and negative weights kind of cancel out each other. Yeah. All right. So let me clean this up. And then I think we have, I think I just give you a case 10. All right, so now let's see if we have 10, we fit like 10 bells, not like 30, not 20. So this looks like pretty good, but still, I mean, here in this type of regions, and the model still cannot behave like pretty wildly, right? I mean, the really large weights in one bell, and then this neighbor got a really small weights. And hope this should give you a very good understanding about what's going on. And I think this is all I want to talk about. Let me see if I have more slides. Talk about RBF kernels, and also even more. I mean, it's just not just bell shape. You can also go really like just piecewise linear, like this. There's actually nothing stops you to do it. So there's some other kind of, you can do this, right? This is another extreme type of basis functions. And even more, you can also do other quadratic, so, or even piecewise linear, like not what I did, this is so extreme, right? You can also, assuming like this region is a linear, I use a linear basis, and this region I'm using linear basis, and that's also, it's a pretty popular approach too. Okay, all right, so this is all I want to talk about.